This is a very basic work about Dickson's formula to establish the Pythagorean triples. First, Dickson's attempt was just algebraically, and we tried to establish methods geometrically to build these triples, and it was an attempt of studying the last Fermat theorem. So we came to his formula because, like Ramanujan tried to, if you try generalizing the problem of Pythagoras for other dimensions, so you come to the last Fermat theorem, okay? And by the binomial, okay, so let's start. By the binomial formula, we can state this illustration to show all the perfect squares in a cumulative form. Like if you sum the first line to the end line, you have n squared, and okay, so we can divide these lines with A, B, and C, showing exactly which is A squared, B squared, and C squared. If you look the entire triangle, it shows the C squared, and the first little one, A squared, and this last trapezoid here, if it is equal to one of those triangles, so it shows the Pythagoras theorem. The proof, let's get to the proof. Okay, so we start by this illustration. You have U, V, and X. And what I try to show here is that if this diamond here has the same content of this triangle here, so this illustrates perfectly one Pythagorean triple. And the Pythagorean triple will be formulated by V plus U plus X equals the C of the original formula. The V plus U will be the A, and the other will be the third V. Okay. And we make this arrangement like the illustration. You can see that the diamond here, his content is 2 times U times X, which is his height, and the content of this triangle formed by the V line, it is a perfect square too. So it shows this formula right here. Okay, V plus U plus X squared minus V plus U squared equals V plus X squared only and if only V squared, which is the triangle in the illustration, equals to the diamond 2 times U times X. The difficult procedure that we try to approach here is to take this illustration to another dimensions, to higher dimensions, and show by a combinatorial way that the figure which will be related to this diamond will never be equal in the content to the triangle, which in higher dimensions we hope would be, you can choose like a half cube. It would be a half cube in the third dimension. Okay, so it comes to the Dickson's formula because of this statement that the diamond equals to the triangle. It is the same statement that Dickson's made about the A, B, and C in the Pythagorean formula, which comes to this formula like here. It's exactly the same. And we hope that if you take this problem to another dimensions, you could approach the last Fermat theorem. And I hope you could, after, take a look at this and avoid this problem in a geometrical view. Do you have any question about the illustration? You can see it clearer?
Sorry, I'm trying to keep up. So I understand that 2 times u times x, that's this kind of diamond part, as you mentioned,
Yes.
on the lower section of the diagram.
Uh-huh.
And the triangle, is that just for the very tip top, or is it the trapezoid in the middle, or is it the whole big triangle?
It's this one here.
Oh,
because-
that narrow slice.
Yeah.
Okay, so kind of like top.
Yes.
to down.
Because
Okay.
in this illustration, if you have any triangle starting from 1
Mhm.
to any other place,
Uh-huh.
it will be a perfect square.
Okay.
It is a very classical version of the problem. It was created, I think, in ancient times. And Dickson never approached to the problem by illustrations or geometry, just algebraically.
Yeah.
So is that why I think it would give us a very clear vision of last Fermat theorem? Because the problem, if you attack the problem only algebraically, you lose the intuition of the problem.
Okay, so
So-
it's that little triangle.
yeah.
It's all contained in the second bit.
Uh-huh.
Okay.
So it would be like this. You have this triangle summed to this one equals the entire. When it can happen, if you sum this one to this other, you have summed this part 2 times, okay? But this one, it doesn't fit it yet. So what you gotta do, just take this content which was duplicated and take it from here to there. So the problem is solved. And it happens only and if only v squared equals 2ux, which is the same two-state Dickson's formula. It's really basic after done. And it's finished. If you could take this copy. It's very simple. Thank you.
Any questions for Lawrence?
Very little.
Sorry.
Hi.
I mean, I can understand, but this would be a bit easy to see in 2 dimensions, but in 3 dimensions, I'm having these are 3-dimensional form.
Okay, if you have 3 dimensions, it would be like a cube. You shouldn't take half of the cube, like this, and his content would be 1 at this face, and all the other part would be 2. So it's exactly the same. It would be easy to make the illustration. The problem is that when you try to fit that part which was duplicated in the 3rd dimension, you get a really difficult combinatorial problem, and I'm still trying to solve it. And we hope that after you could generalize to any dimension.
Any more questions or comments?
So, but no, 6.
Okay, thanks again. Now at 5 we have Isabella Novik speaking, plenary session.
Thank you.